Today is December 2nd, 2011. This is the continuation of the 7-2 lecture for AC Stats at Berkeley High School. We are going to focus today on the sampling distribution of p hat. And again, let me try to describe again what sampling distribution is, and then in particular, what is the sampling distribution of p hat. Sampling distributions come about when you do all possible samples of a particular size from a population. Sampling distribution of p hat is when you do all those possible samples, you look at every possible p hat which can come out of that population. Since not every p hat is going to be the same, since not every time you do a random draw from a population will you get precisely the same number of left-handed people, or precisely the same proportion of females, or exactly the same proportion of heads when you flip the coin 100 times. Because there's going to be variation in each sample, p hats vary and have a distribution. Remember, back to our beginning days, what's a distribution? The values that a variable takes on and how often it takes them on. Yesterday we looked at some graphs, the graphs of the distribution of orange colored candies out of a population of candies. So we need to sort of summarize what we saw yesterday. We need to summarize what did we see when we looked at the distribution of p hat. And we're going to think about it in terms of those big four ideas. SOCS, shape, outliers, center, spread. All right, let's talk about the shape first. The shape of the distribution of p hat can be, not is, can be approximately normal. Sometimes it's a little bit skewed, but if we look at the distribution, when we meet a particular condition, it is normal enough for us to use the normal distribution tables. It depends, though, on how big our sample is and what the proportion at the population level is. It depends on N and P. Sometimes it can be normal. And normal is good for us because we have a lot of tools that we can use if we encounter a normal distribution. The center of the sampling distribution of p hat is always p, the population proportion. If 15% of the population is left-handed, the sampling distribution from that population will have lots and lots of different p hats. But the center of all those p hats, the mean of all those p hats, will be at 15% also. As long as we have an unbiased way of sampling. If you saw a note on your quiz the other day, how do we get unbiased sampling? Answer, by doing random sampling. Specifically, simple random samples. What about the spread? Well, we noticed as sample sizes got larger, the spread got smaller. The more and more we put into the sample, the tighter and tighter each p hat seems to be around that population proportion, around p. As n gets larger, the standard deviation gets smaller. The actual value of the standard deviation, though, is going to be dependent on how big your sample size is and what the population proportion is. Which leads me to stop for just a second. Can we just review one more time what's the difference between P and P hat? Because it's a really important distinction that we need to make before we go any further. What's the difference between P and P hat?
Isn't P population?
P is population. Okay, give me a real life example though to show me that besides just knowing the keywords, the buzzwords, what is that? What's that key difference?
Like population. Population of cats in America.
Okay, population of cats in America. Huge number of cats in America.
Oh, much.
So much too large to actually interview every single one of them. And even if you did interview them, what would they say? Yeah, right. Okay, so Jason has defined a really big population. Okay, now tell me about your, sorry. I just heard a really bad joke just runs through my head. Tell me about the cat P. Cat P for proportion. Cat P. Okay, so tell me about the P related to the population of cats in America, Jason.
So like you want me to tell you P hat?
Well, tell me about, what is it about the cats you're measuring?
We measure how many cats run away from home.
Okay, and that's a categorical variable, is it not? You look at the cat, have you ran away from home, or have you not ran away from home? It's a yes or no answer. Definitely categorical, definitely appropriate for a P measurement. Keep on going.
Turns out that 64% of cats run away from home.
And that's really funny because Jason knows that exactly 64% of all American cats run away from home. But indeed, we have to make this leap of faith. Somehow we have population knowledge. Okay, so Jason knows that P is 0.65, all American cats. Okay, but what's P hat?
No?
What's P hat in this example?
0.64.
No. If you were able to know the number of cats that run away from home from all the cats in America, we're declaring that to be 0.64.
Right.
That's a P value.
P value.
Let's compare and contrast that with a P hat value.
Just the cats in Berkeley.
Okay, so the cats in Berkeley is a subgroup of all American cats. And so, the proportion of cats from Berkeley who run away from home, Kyle, which is 54%,
54%. That's P hat.
is a P hat. Excellent. Excellent. Well done. Well done. That is indeed an example of a P hat. By the way, the best P hats, though, come from random samples of the population. Interviewing only Berkeley cats may be a biased sample. Or interviewing only cats in Oakland County may be a biased sample. Because you know what? The cats in Oakland County, they don't want to leave their warm homes during the winter. Those Southern California cats, boom, they're gone. They're going to the beach. Which they just call one really large
Are we talking about
litter box.
Are we talking about cats like animals or cats like cool player pimps?
Jason, would you like to define your use of the word cats?
Someone cats like animals.
Okay.
Not like
Not like,
Like meow.
yeah, like meow. That's like when we interviewed the cat, they said meow. They didn't say.
meow or a no meow.
Yeah, that could be. All right.
Pimps say meow.
Okay.
No, not gonna get this conversation.
Say meow to the host.
Maybe there's a typo in this slide. There is
I'm glad
an important connection.
Yeah, it should be an important connection, not and important connection. Good thing I didn't type this, but I am responsible for the quality of the presentation, so my fault. All right, so there's an important connection between the sampling proportion P hat and the number of successes N or X. So when we interview N cats and we ask them, have you run away from home? We get the value of a random variable, let's call it X, and P hat is the value of the random variable divided by the sample size. So Kyle, you interviewed 100 cats. and 54 of them said they had run away from home? Okay. Or it could have been 200 cats and 108 of them ran away from home. How did you know 64% of the cats in the United States ran away from home? I just making stuff up. Okay, are we okay with that idea?
Use it after that.
There's an after that. All right, so those are really, really general statements about the sampling distribution of p-hat. Now, our job from here is to get more particular, i.e., some of the times the sampling distribution is normal. When is that some of the times? We know that the center is always the value of p. That's really good. That's a good, solid piece of information. Let's log that in. Last one. We know that the standard deviation does get smaller as n gets bigger, but can we get more particular on that detail? Can we get an actual formula that will tell us about the sampling distribution's spread? Well, let's see. Does anyone require more time on this slide? No. So let's continue on. Let's start with something that we do know. We had learned in the previous chapter about the binomial distribution. Right? The binomial distribution had those 4 criteria. Every trial ended either a success or a failure. Every trial was independent. There was a set number of trials, and every single trial had the same probability of success. Do you remember those 4 criteria? BINs, I think, is what we summarize them as. There seems to, in my mind, something really similar between binomial and p-hat. And the idea is this. In a binomial distribution, every trial ends in a success or a failure. That is kind of like a categorical variable. It ends in either a yes or a no. Either you interview the cat, yes, I ran away. Have you ever tasted cat food? I'm out of here. Or you interview the cat and say, no, I didn't run away. Warm home, I'm sticking close to home. So every time you interview a cat, it's like a success or a failure. And the random variable x, then, from that binomial situation, is like counting up the number of successes that you would then divide by the number n to find the p-hat. So, if we combine a couple of ideas from the previous chapter, we're going to get some insight. One idea from the previous chapter was, okay, one idea from the previous chapter was that the mean of a plus bx is equal to a plus b times the mean of x. Do you remember that? One of the big 6? Okay? When I convert the number of successes, x, into a p-hat, it's like doing this linear transformation. X divided by n. How would I do, if I had a random variable x and then I divided all those random variable x's by the number of trials, I no longer have whole number x's, I have proportions now. X divided by n, 1 divided by n, 2 divided by n, 3 divided by n. Converting a binomial distribution into a p-hat distribution is like dividing by n. Well, that would suggest that this expression, which is equivalent to the mean of p-hat, is equivalent to the mean of x divided by n. All right? If I only knew what the mean of x was, if I only knew what the mean of x was, I do. It's NP. So this is equal to NP over N. Oh, this is equal to P. Wait, we already knew that. On the previous slide, we said that the mean of the distribution of P hats is exactly P. Okay, so we now showed some mathematical wizardry that confirms that. But let's do the next thing. We know, as we said by looking at those graphs, that the larger the sample, the smaller the spread. Let's do that same calculation again. Let's do the same calculation. I want to find out what is the standard deviation of P hat. And from the previous chapter, one of the big 6 formulas was really about variance. So let's say I really want to find out the variance, and then I'll, Jason, what will I do to go from the variance to the standard deviation?
Root that.
Thank you. And then I'll take the square root of both sides, and then I'll know what this. All right. So what is the variance of P hat? Okay. Well, maybe I should restate that. What is the variance of x divided by n? Here's the formula that I'm using. I think we also had another formula in there that looked like this. This is a plus bx. Which one do you want to use? Which one do you want to use? I usually over the last 7 years I taught it this way, but I'll do it this way. I'll do it this way. All right, we'll get rid of the variance. All right. So the standard deviation of P hat is equal to the standard deviation of x over n, which is equal to the absolute value of 1 over n times the standard deviation of x. Again, standard deviation of x is the x that's coming from a binomial situation. And as we had learned before, the standard deviation of that is the square root of n times p times 1 minus p.
Really sorry. I don't know how. It goes perfectly.
All right, now, last part. Can I clean that expression up a little bit? 1 over n times the square root of n times p times 1 minus p. Well, if I bring this n inside there, I get the square root of n times p times 1 minus p all over n squared. The act of bringing the n inside the square root makes it an n squared. And now I can clean that up one more time, and I get the square root of p times 1 minus p all over n. All right, get your formula sheets out, please. Get your formula sheets out, please. Okay, I want you to get your formula sheets out, and I want you to look on the page that has 2 boxes that are shaded, where the header of the boxes are shaded. In the first set of boxes, it says single sample above the box, and then inside it says sample proportion inside the box, and then it says the standard deviation of the statistic is the square root of p times 1 minus p divided by n. So we just derived it. We saw that something like this was going on, in that when n gets larger, what happens to that fraction inside the square root? As n gets larger, the fraction gets smaller, and then we take the square root and it gets even smaller still. So this is the formula that allows us to say what exactly the sampling distribution's spread is. So let me wipe out all my drawings, and let's see how they summarized it. Okay? The center mu of p hat, the sampling distribution of p hat, the center of p hat is equal to p. As long as p hat is an unbiased estimator of p, meaning it's coming from a random sample. The standard deviation of p is equal to the square root of p times 1 minus p over n. In other words, as n gets bigger, the standard deviation gets smaller. Well, I mean, it's on your formula sheet. You know what it stands for? I don't care how you get it in here. Write it down if you want to write it down. But have it here. Okay? Are we okay with that? Are we okay with those ideas? These are really big ideas. Really important ideas. All right. May I go to the next slide? All right. So, here's what we know about the sampling distribution of p hat then. If we're using a simple random sample of our population, and I want you to right now tie these ideas together. Simple random sample means that the samples are unbiased. Unbiased means that the center of the sampling distribution is going to be the same as the population proportion. Okay. If we have a simple random sample of size n, and we declare p hat to be the proportion of successes in the sample, then the mean of all those different p hats that can come out from all those different samples is p itself. That the standard deviation of all those different p hats is going to be the square root of p minus, or times 1 minus p all over n. And that's true as long as the 10% condition is met. Okay, I didn't bring this up on the previous slide, I probably should. What do I mean by the 10% condition? I mean this. We know that all that work we just did deriving this formula was based on the binomial distribution. Remember, I started with the binomial divided by n. The I in bins stands for independent. So embedded in binomial is an assumption of independence. But, like we demonstrated and talked about with the card metaphor before, when I pull one card out of the deck, the proportion of red cards changes. We don't have independence. But, again, if we imagine lots and lots of decks of cards, while the proportion of red cards changes, it changes so little that it's immaterial. Doesn't matter. If the population is much, much larger than our sample size, we have enough independence that we can use the formulas. So, we may use this formula, which depends on the independence of the binomial condition, as long as we're independent enough. As long as n is less than or equal to 1/10 of big N, where big N is the population size. Now that's the way the book summarizes it. I actually prefer this notation. As long as population is at least 10 times sample. That's the notation that I use. As long as the population is at least 10 times the sample size. We're independent enough. Lastly, n is large enough, the distribution of p hats is approximately normal. Because we talked about the center, we talked about the spread, let's talk about the shape. If n is large enough, the distribution of p hats is approximately normal, and that's really good because we got these great normal tools. We got the normal distribution probability table. We've got the normal CDF built in our calculator. We want things to be normal because it makes the calculations really, really easy. How big is big enough? Answer, as long as there's at least 10 successes and at least 10 failures. N is big enough. Say that one more time.
Stuff in my head, I'm just spinning.
Okay. So, we can, to summarize, we know always, always, always the center of p hat. We know sometimes the standard deviation, as long as we meet this population is at least 10 times sample condition. And we know the shape as long as we get at least 10 successes and 10 failures from our trials. All right? That we expect at least 10 successes and we expect at least 10 failures. That's when n is big enough. Are you okay with those really, really big ideas? I'm not sure I am really successfully selling the idea that this is huge, this one page of information. Really, really important. Like, oh my gosh, that big. Okay? Have I made my point now?
Yes.
Like, this is it. This is big stuff. All right. Can I go to the next slide?
No,
Because what?
yeah.
Not yet.
This doesn't really help us on the homework, though.
It doesn't?
No, I thought what helped on the homework, like, when we went over the quiz, we went over, like, actual problems. I felt like you taught the lesson then, as opposed to just lecturing us definitions.
Okay. Well, I think the next step is we're going to try to apply all these ideas. All right? I think that's where we're going next. So I want to get to the application stage.
I know, because it's like yesterday, like, I felt like I really learned something when you taught it to us, but not
Okay.
just
Well-
all that book stuff.
Well, let's try to apply this, and maybe we'll make that same jump. All right. You ready now? All right. So, last way of summarizing it. Got a big population. I can pull a simple random sample of size n, and I get a p hat. I can choose another simple random sample and get a different p hat. Do it again and again. I get p hat after p hat after p hat. I get every p hat possible from that population. Some of the p hats, some p hats right there. Hey, that p hat's really close to the population mean. This one got really far away. I get lots and lots of p hats, but I get many more p hats in the center than I do farther and farther away from the population proportion. It's rare for me to get way out there. It's very common to get things that are really close to the population proportion. The p hats have a distribution. The distribution is centered at p. The distribution spread can be calculated using the value of p and n. And the distribution is normal as long as np is greater than 10 and n times 1 minus p is greater than 10. Oh, sorry, it's approximately normal. It's normal enough that we can use the normal tools. All right. So let's do a problem. Polling organization asks a 1,500 first year college students how far away their home is. Suppose that 35% of all first year students actually attend college within 50 miles of home. I'm going to stop right there. We have some numbers there. We have 1,500. We have 35%. Okay? What is 1500 in our variables, in our symbols? N, sample size. What is 35%? P, pretending that we have information about all of the first year college students. In the same way that Jason made up that he knew about all cats in America. 35% at every single first year student. Okay. What is the probability that a random sample of 1,500 students will give a result within 2 percentage points of the true value? Okay. Now, this is a 4-step process, and I'm really going to start forcing you to do a 4-step process in my particular way. I make a box. I make 4 boxes. And here's where I put step 1. I want to state what is it that we're trying to find. Probability that P hat is within 2%. And I'm not going to say the true value. What I'm going to say of P, because P is the letter that we mean, or we use when we talk about the true proportion. All right. So in step 1, what is it that we're trying to find? Step 2, how are we going to find it? And I've got an idea. Let's use the normal distribution to find this answer. Let's use the normal distribution to find this answer. Okay, now let's double check what we know. Do I know what the center of P hat is? Yes? What is it according to the notes that you wrote down just a few seconds ago? And I kept on saying that it's really, really important. It's P.
Over 1 minus P divided by N.
No. The center of the P hat distribution is just P, the population proportion. Or in this case, 0.35. Do we know what sigma is? Sigma of P hat. Do we know what sigma of P hat is? No, Jason, you just gave the formula.
Oh yeah, P times 1 minus P divided by N.
Okay? Or in this case, it is the square root of 35% times 65% divided by N. 1,500. Great. What about the shape? What's the shape of P hat? The distribution of P hat. I really hope it's normal. Can you give me a convincing argument that it is? Remember the conditions that say that we can say it's normal if we expect at least 10 successes or 10 failures. If I interview 1,500 people, I ask them, do you go to school less than 50 miles away from home? Can I expect out of 1,500 people, at least 10 people to say yes? If I ask 1,500 people, do I expect at least 10 people to say no? Out of 1,500. Okay. The shape is normal. Why? And this is how number of successes is NP, and that's greater than 10. The number of failures is N times P minus 1, and that's greater than 10. Oh, I'm sorry, I forgot something here. Right there. I forgot that I can't calculate the standard deviation unless I know I have independence. What was that condition for independence? Population is at least 10 times the sample size, or 10% of the population is bigger than our sample size. Is the population of college students greater than or equal to 10 times 1,500? Do we think the population of first-year college students is bigger than 15,000 students? Heck, there's almost 15,000 freshmen at Michigan State in any given year. So, do we have that?
Yeah.
Sure. So we have independence, so we can say that. We have at least 10 successes and failures, so we can say that. Okay, step 3 is over here. Okay, what's step 3? Ready? Let's go ahead and finish the calculations. I'm going to draw a little picture too. Here's a picture. It's a normal curve. I know it's normal. We check the conditions. The center of that normal curve is 0.35. The standard deviation of that normal curve, and again, this is the curve of all p-hats. I don't know, can someone in their calculator give me the square root of 35? 0.35 times 0.65 divided by 1,500? 0.0118. Great. All right. Now the last part. What's the question that we're trying to answer? What's the probability that p hat would be between 33% and 37%? Which is just another way of saying within 2 percentage points of the true value. I'm thinking a z-score is in order here. What do you think? I really wish I could remember how to do a z-score.
Wrong.
Isn't it like standard deviation?
Actual minus mean over
Actual minus mean. What's the actual that we're looking at? 33. What's the real that we're looking at? And what's the standard deviation of that? Okay. Negative 1 point something. Help me out, please.
Negative 1.69.
35?
6949.
Oh, 654. Okay, 65. All right. And by the way, on the other end, I can put the numbers in, but it's just going to be the positive version because they're exactly the same distance above the mean. Okay, what's the last part of this? Subtract.
Well, you gotta find the percent values first.
Okay, find my values. Find the values associated with these z-scores, please. I'm going to say it's either 0.8 or 0.9 is the upper end.
Lower end is.
I'm on upper end first. All right.
9505.
One more time, Abby.
0.9505.
9505
Nice to see.
minus 0.0405.
0495 for the lower end.
0495. Whoops. Okay. Giving me a total of 0.9. 0.9010. Okay, great. I finished the calculations. What's step 4? The hardest part. P-R-E. Interpret. What does it mean that what we just found? If we do repeated sampling from this population, 95% of the p-hats that we get will be within, sorry, not 95, 90 90.1% of the p-hats we get will be within 2 percentage points of the real answer. If we do repeated random sampling from this population, 90.1% of all the p-hats will be within 2 percentage points of the real proportion. Is that okay? Great. I think that's where I want to leave that off. We don't want to do that. Okay. We're at the summary slide. How much time do we have left? About 16 minutes. Okay, here's what I want to do. No, here's what I want to do. That one example, I don't think is sufficient. All right? So what I think I'd like to do, instead of going on the summary slide, and the summary slide's got great information in all of it, what I think I'd like to do is I'd like to take one of your problems from your homework, and let's do another problem. All right? So does anyone have written down what the homework assignment is?
Yeah.
All right, and let's do another problem from the homework, and
There's like hills there.
okay, here we go. I'm going to read the question to you. I'm actually looking at problem number 35. Is 35 in your homework? Okay, great. This is a very important issue, especially for my brother-in-law who works at Kellogg. Problem number 35 asks the question, do you drink the milk after you eat your cereal? A USA Today poll asked a random sample of 1,012 U.S. adults what they do with the milk in the bowl after they've eaten their cereal. Of the respondents, 67% said they drink it. Let's suppose, okay, by the way, let's suppose. Do you know what the word suppose means? What after follows suppose? I'm making this up. Suppose 70% of U.S. adults actually drink the cereal milk. Let P hat be the proportion of people in the sample who drink cereal milk. All right, so let's start there. What's that? This is number 35. Okay, again, I'm going to start pushing hard. I want you organizing your solutions in this 4-step process. All right? Let me read the last part of the question. Find the probability of obtaining a sample of 1,012 adults in which 67% or fewer say that they drink the cereal milk. All right? So, step one. What are we trying to ask? How often is P hat less than 67%? might even put in other things. P hat is proportion of adults who drink cereal milk. Just to say, give a little insight on what we're doing. Okay? There's step one. What are we trying to find out? Step two. How are we going to do it? I say again, we're going to try to use the normal distribution.
Where does that percentage 70% come in place?
Someone made it up.
Are we gonna
Remember
use
the word suppose?
Yeah.
Always following the word suppose is something that's made up.
So we shouldn't have.
Suppose I could fly. That kind of thing. I'm not kidding you. I want you to have that mentality. Anything that follows the word suppose is something that's being made up.
Okay. So we shouldn't really.
Trust me on this. All right. All right. Normal distribution. Can we use a normal? Put it a different way. Is p hat is the distribution of p hat normal? Before we can use normal distribution tools, we got to confirm that it's normal. I don't know. What did we say about proving or having something being approximately normal for these kinds of situations? Are we going to get at least 10 successes? What do we mean by success in the context of this problem? They do drink their milk. Do you think that we interview 1,012 people that will get at least 10 people who drink the milk? Sure.
And when we get 10 people that don't drink the milk, so it's normal.
Oops, I spelled failure. So Jason says it's reasonable to think that we get at least 10 people who don't drink their milk. You know what they do with the milk? They give it to their cats. We're back to the cats thing, I guess. Yeah. Okay. So I think we're good here. Is the distribution normal? Yes. Hey, I got another question. I would like to use that formula for the standard deviation of p hat. Do we meet the conditions for it?
Yes.
What is that condition?
Population is greater than or equal to 10 times.
Okay, you know what? I want to start using this notation for this. Because really, when I ask that question about can I use the standard deviation formula, I'm really asking the question, is there enough independence in the way we're doing things? Abby says population is at least 10 times samples. The population is like all American adults. Our sample size is about 1,000. Is it reasonable to think there's at least 10,000 U.S. adults?
Yes.
Not even restricted. All adults. Sure. Population is indeed greater than 10 times sample. Check mark. That means we can use that formula for standard deviation. I'm going to go down to the calculation phase if you don't mind. The distribution of p-hats is approximately normal. It's centered at 0.7. Why? Because we supposed it's 0.7. We made that up. And it has a standard deviation. And that standard deviation is going to be the square root of 0.7 times 0.3 divided by 1012.
That's standard deviation, 1,012.
I can't hear you.
Is that the standard deviation, 1,012?
No, the standard deviation is this whole square root.
Oh.
Again, because we're using that formula, sigma of p hat is equal to the square root of p 1 minus p over n. All right? You want to calculate what that real number is? Can someone take the square root of that whole yucky stuff? Anyone? Come to my rescue? 0.0144. Great. And now I'm ready to ask the question in symbols. What's the probability that p hat is less than 0.67? Maybe I can even draw a picture. Here's 0.7. Here's 0.0144. And then we're down like here at 0.67. And we're interested in what's in that little tail. Sometimes the picture is helpful. All right? So how do I calculate that? Calculate the z-score maybe? I mean, we do want it to be normal, so we can use the z-score and use it in the table. How about the z-score is 0.67 minus 0.70 divided by 0.0144? Negative 2.083. So negative 2.08. So this proportion is equal to the proportion of z-scores that are less than negative 2.08. And that's nice because that's that's just the way the table's written. We look up 2.08 on the table. Going to be something like 0.0188. Okay? Are we okay with that? All right. Step 4 is, again, interpretation.
So 0.0188 is an answer.
That's the, well, but we got to, in the interpretation, we finish off the whole answer. The probability of a random sample of U.S. adults being 67% or lower is 1.8%.
Isn't it 1.9?
1.9. Okay. You're right. Boy, that's really rare. That's really rare that I would do a random sample of U.S. adults, ask them that question, and I would get an answer of 67% or less. I think that's evidence to something. I think it's statistically significant because it's so rare. I think the thing that we supposed is wrong. I didn't say that, Ned. We'll get there later. All right, so you have a big old homework assignment. Having to do with 7-2. It took a lot of time to get here. Okay, I will be in early on Monday because I am going to guess that at least 5 of you are going to be frustrated by the homework over the weekend. in early on Monday as I am, always, but I think I'm probably gonna see some